Hi friends, a very good morning and thank you everyone for joining in. Let me just verify if everything is working as expected before we jump into the live session itself. Just give me a couple of minutes. That's the reason I typically try to join a few minutes early to ensure that everything is working as expected. Let me just...
Hi friends.
Yeah, I see that everything works as expected. Yeah. So again, since this is on YouTube, it's open to everyone. You should be able to watch it on any device of your choice. Hey, good morning, folks. Thank you for joining in. And yeah, so since I'm a little early, let's wait for others. And since many of you are a little early, let's wait for others to join in. And in the meantime, we have, I'll start the session itself at 10:05, which is 5 minutes past 10. So in the meantime, if you have questions, please shoot them into the chat window. I'll try to answer as many as possible. Hey, good morning, folks. Thank you. So somebody says, please create a separate course for live sessions only. The problem with that, again, it's a good suggestion, no doubts about it. The only problem is for many of our live sessions that we do for our registered students, we go back and refer to the course videos a lot. So if you have not gone through the course videos, you may not be able to understand it, whether it is notation, whether it is code, whether it is mathematics. I try and connect back to concepts that I have taught earlier in the course videos, right? That's why I don't know how this can be worked out, but I'll surely discuss with other students and our whole team and get back to you. That's a good suggestion. Thank you, Nirvik. So somebody says, give tips for campus placements. Again, depends on the placement that you're sitting for and the type of company that you're attending. At the end of the day, if it's a software development role, you have to be good with programming, data structures, algorithms, whether it is services companies, small companies, or world-class top-tier product-based companies. Most companies typically focus on programming, data structures, algorithms. There are some companies which also focus on simple aptitude, which is nothing but your pre-10th class mathematics, right? So yeah, so you at the end of the day, you have to be good at least one major programming language, basic data structures and algorithms that you study in your BTech first year and second year. Bottom line, that's what it is, right? Somebody says, how do you deploy BERT GP2 in real time? Size is challenging. Yes, it is challenging. So one suggestion that I suggest for people who want to use BERT-like models is either use a cloud API, like Google API can give you these BERT-like vectors. Again, if you want to really deploy it at scale, you will have to use some cloud-based system and large array of GPUs. That challenge certainly exists. So if you have dedicated GPU-based hardware, that's okay. But otherwise, it's best to use cloud-based systems. Either you host your own systems on AWS or Google Compute Platform or Azure or IBM Cloud, or you just make API calls. So amongst all the cloud service providers, one of my favorites as far as machine learning APIs is concerned is Google GCP. While Google Compute Platform may not be very good for other tasks, for AI and machine learning based APIs, it's one of the best out there. So you can just give your, you can just make these cloud API calls to get some of these vectors, or you can build your own cloud-based infrastructure, because on AWS, Azure, Google Compute Platform, you get GPU instances, right? That's the best way to deploy, to be honest with you, especially if you have high compute deep learning models with a lot of compute requirements. Okay. So somebody says almost all companies attend your campus. Okay, we're talking about campus placements. My suggestion is this. Okay, so I mean, there are tons of resources on the internet where you can find interview questions asked at the company that is visiting. Let's say Amazon is visiting. Just Google search for Amazon SDE interview questions. Right, you get hundreds of them. Try to see whenever you're preparing for these software development engineer interviews, please make sure that given a question, typically a data structures or algorithms question, you should solve the whole question, including code, in 20 to 25 minutes. That's a typical expectation from the interviewer, especially for an SDE1 role, right? So you read a problem, the problem might require dynamic programming, some graph algorithms, some data structures, whatever it is. Read the problem, it will take you a couple of minutes, try to come up with a good solution with a decent time and space complexity, right? And then implement it. You should be able to do this whole thing in 20 to 25 minutes. Because typically for most of these interview questions, the code required is not humongous. If you use a modern programming language like Java, Python, even C, C++, the code will not be more than 30 lines of code, right? So what the biggest mistake I see a lot of folks do is they don't practice coding. But the interviewer says either go to a whiteboard and write code, or they'll give you a document and say type your code here, right? So there are people who practice these questions, read an answer, come up with the algorithm, but they don't write code. But in the real world, writing code is as important as coming up with the code, coming up with the algorithm or the solution with good time and space complexity. Number one. Number two, when you're writing code, please make sure to handle the boundary cases gracefully. That's a very important thing that is expected out of entry-level software engineers. Okay. So before we dive in, folks, I may not be able to answer all the questions because of constraints of time. So if there is anything that I'm not able to answer, either in this open-ended session or in the live session, which is related to big data storage technologies, please shoot an email and we'll respond back to as many as possible, as early as possible, right? So, okay, what are these questions? Okay, so again, folks, please avoid typing the same question and again, because you're just occupying the space in the chat window. Like Vishal asks a question, but I don't understand what this question is. Can you discuss the basic idea and frame of work and tool which will be performed? So I don't understand that question. So anyway, I'll look at the other questions. So somebody says, do you have plans for a full stack developer? Again, we are looking for phenomenal instructors to do these multiple courses. As and when we find a good instructor, we are certainly keen on starting a full stack developer course also. But currently, we are still on the lookout for some good world-class instructors with great experience and real-world knowledge, right? So as a stat student, this is a very good question from Gautam. So as a statistics student, how can I compete with BTech or engineering students? So to be honest with you, stat students, I'm assuming you're not just a B-stat, but you also done your master's in statistics or MSc in statistics, or as some universities give, it's an MStat or an MSc statistics. So as far as machine learning data science roles are concerned, an MStat with good programming knowledge is equivalent to a BTech in computer science with the statistics and the data science knowledge. Actually, there are roles for which MStats and MSc statistics and mathematics folks are preferred than BTech computer science, because BTech computer science folks are very good with, expected to be good with programming data structures algorithms, but not as much with statistics. But MSc statistics folks are expected to be very good with statistical analysis. So if you're an MSc statistics student, please try to become good at programming basic data structures algorithms, nothing too advanced, basic data structures algorithms, and you should be able to compete with BTech CS folks for data science and machine learning roles fairly easily, because your depth of knowledge of statistics is significantly more than a typical BTech, whether it's computer science or any other department. Even ECE folks, you're supposed to be better than them because you've studied statistics and applied mathematics and core mathematics or pure mathematics itself much more rigorously than a CS student. Okay. So somebody asked a very good question, Rohit. I'm a bit confused. If you get a role where your compensation is less than your current role, but you get a role in machine learning data science, should you take it or not? That's a very good question. You should first, if the compensation that you're being offered for a data science or machine learning role is less than your current comp, first you should talk to the recruiters and say, folks, you should at least match. Okay. So try to get it to the matching level so that you're not taking a financial hit, number one. Most companies would at least match, number one. Number two is the potential to grow in data science machine learning roles is significantly more than other traditional roles which have been there for a long time. For example, imagine if you are a QA engineer or a testing engineer, right? So if you're a QA engineer, your potential to grow will be significantly less, both financially and in terms of career, than a data science or a machine learning folks, right? So let's assume you're a QA engineer making, let's say, 10 lakhs per annum. I'm just making some numbers up, right? With some experience. Suppose somebody offers you a machine learning job with, let's say, 9 lakhs per annum. Just talk to them and tell them, at least match my comp. When they match your comp, right, you're not losing on it financially. Now, from 10 lakhs with some experience, right, and by building on top of your skills, you can certainly grow significantly faster as a data science guy than as a QA guy. So if you look at it, even if you get the same compensation, if you look at it from a 5-year horizon perspective, you'll be much better off from a data science role. So a lot of people do this mistake. They look at compensations as a one-time jump. Please don't do that. You should look at compensations and growth from a slightly long-term perspective, because most of us will have a career of at least 35 to 40 years, right? So don't just say, okay, hey, I'm not getting a hike here, so I won't go. Probably the role is so good that you get to learn so much and you get to grow a lot. Again, this is my own career. From my own career, I have made choices where I got slightly lower compensation, but I got terrific roles where I could grow and learn a lot, and I picked those roles. Like when I joined Amazon, I had competing offers from other top tier product-based companies where the compensation was slightly better than Amazon. But at Amazon, I was one of the earliest machine learning scientists in our whole org. So I knew that this will be more like a startup where I get to learn a lot and grow a lot. So in the long run of a 5-year time that I spent at Amazon, I got to grow a lot. I got to learn a lot, which I may not have had if I joined another company where I had a competing offer with a slightly better salary. So please try to look at your career from a longer lens, from a 5-year horizon rather than the instant jump. That's very important. Somebody says, does Amazon hire freshers for ML role? Yes, there is a role called Applied Scientist 1. Okay, there is a job family called Applied Scientist. There is a role called Applied Scientist 1, which is parallel to Software Development Engineer 1. That's where most freshers are hired at Amazon for machine learning roles. Freshers who are typically bachelor's or master's degree holders, typically PhD students tend to join at Applied Scientist 2, right? And from Applied Scientist 1 to 2, if you work for a couple of years, if you deliver good results, you can easily go from Applied Scientist 1 at Amazon to Applied Scientist 2. Typically, PhDs join at Applied Scientist 2, right? So that's to give you a sense of it, right? So if you're a bachelor's or a master's degree student, Amazon does hire at Applied Scientist 1, and there are more people there than at higher levels, to give you a perspective there. Okay. This is a good question. I'm recently hearing a lot of imbalance between work and life at product-based companies. How does your experience pan out? Again, amongst product-based companies, there is a huge variance, right? I know I have my classmates, my close friends. It also depends on the company and also the team, right? I'll give you my own perspective. When I joined my team, I was the first machine learning scientist. And I had a very good friend of mine from my Yahoo Labs days, who was my manager, great friend of mine. So we were just building so many things and nothing existed. So we were more in a startup mode. And in a startup mode, we were putting in like 12, 13-hour days consistently, day in and day out. There was a lot of work pressure, but there was also a lot of potential to learn and grow, right? So there were a couple of years when we were in that mode. But as our team grew, as our team grew to a massive team, spread across both Bangalore, Silicon Valley, and some folks in Seattle. As our team grew, the workload reduced, but more managerial effort started coming into our shoes, right? So no team will be always boring. No team will always be like crazy workers. But compared to other companies, Amazon and Facebook tend to be more I wouldn't say workaholic, more work-oriented, where there are very strong measures of performance taken into consideration as compared to other product-based companies, right? So we often joke that people who survive Amazon for 1 year can comfortably survive for a very long time, because the expectation, Amazon moves very, very fast as a company, right? Again, this could change. I know people in Amazon in some teams who are bored, right? So it's not, I can't draw a single picture for all the teams at Amazon. Some teams, they'll have very good work-life balance, 9 to 5 government job type stuff. There'll be some teams at some periods of time where they'll have to put in 12-hour days. There'll be some teams where, people are like bored. That happens in every company. But there is a higher chance of finding a higher growth and more learning work at companies like Amazon and Facebook. Of course, I'm not saying companies like Google don't have great work. I know teams at Google, I have colleagues and friends at Google who are doing terrific work. Again, it all boils down more to the team than to the company itself. Okay, so let's see. Okay, sounds good. It's already 10:07, so we have overshot a little. So I'll pause this chat-based answering. Let's jump into the live session itself. Let me start sharing the screen. I hope everybody can see the screen. Let me just refresh and check if everybody can see the screen. Just give me a couple of minutes. Okay. Okay, so since everybody can see the screen, just confirm if everybody can see the screen now. Okay, so this is the live session that I wanted. I've written some notes here. I'll give you a lot of pointers. Okay, so I hope everybody can see this. Let me just cross check. Okay, okay. Okay, I hope everybody can see the screen. So let's get started with this. Today's session is called Big Data and Cloud Storage for Machine Learning and AI. Right? So we'll focus on various types of data storage technologies from the 1970s to today, why some of them came into existence. Of course, it's impossible for me to cover everything because, this is typically a multi-semester subject if you're studying, especially at graduate level, right? So this is a massive subject. I know people have done PhDs in these topics. So by no means I can cover everything in depth in this short duration, but I'll try to give you, one second. Let me just check if everything is okay. Yeah. Okay, so there is a screen skew I see. One second. So is everybody able to see the screen clearly? Just let me check. Oh, there seems to be a small hiccup. Just give me a second. I'll just fix this. Just give me a second, folks. Can everyone see the screen? Let me go to YouTube and see if everything is as expected. It's cropping. It's for some reason it's cropping. It's not full screen. Okay, let me just fix it. Give me a couple of minutes. I'll do this. Let me just do this quickly. Or else I also have a PowerPoint backup in case something like this happens. Okay, just give me a second. Let me see how the PowerPoint works in case there is a problem with this. Let me see. So we're not seeing the full screen for some reason. Screen share, display capture. Just give me a second. Just give me a second. Creative Cloud, Finder. None. Okay, is this better now? Let me see. Let me just check. I think this is fixed now, right? So I'm hoping it is fixed. Yeah, the screen share has a small hiccup. I'm just trying to see if the screen share is working as expected. Just give me a second. Just give me a couple of minutes, folks. I'm just trying to set this right. Or else let me start another one. 2. I'll just add the display, display capture, okay, cursor, okay. Okay, mic check, okay. So let me just see if this is better enough. Just give me a couple of minutes. I'm just trying to adjust. Okay, this seems to be working. So let me just do a full screen. Can you guys check? Unable to see full screen. I understand. Is this better enough? Can you guys confirm? I'm in the full screen mode. Okay. Is this better enough? Let me just refresh everything. Okay, not yet. Yeah, so let me. Okay, you're still seeing. Is this better enough? Okay, let me go to OBS. To window, no crop, none. Okay, okay, display capture 2. Okay, this is working. Display capture settings. Just give me a second. None. Okay, okay. Let me see how I can fix this. Okay, I'm trying to adjust so as to squeeze everything in. Just give me a second. I think this is just okay. So I hope we should have this now. Yeah, I'm hoping you should have this now. Yeah, you should be able to see the full screen now. Let me just refresh everything. Just give it a minute. I'll fix it ASAP. This is not about window resizing. This is an OBS bug, so I'm just fixing it. Yeah, so I think it's you're seeing the whole screen. So yeah, so you might see a little. Sorry for that hiccup. I hope we are fixed now. Okay, sorry for those 5 minutes of wasted time, but that's okay. So I'm hoping, just confirm if you're able to see the screen properly. I'm assuming, yeah, you're able to see it. Cool. So let's go into the session itself, right? So I'll take a break in between also. So this session is called Big Data and Cloud Storage. So we'll look at various data stores that are available both in the SQL and NoSQL and big data frameworks. And we'll also look at how some of these big data storage technologies are available on the cloud also, specifically for machine learning and AI techniques. There are today hundreds of special purpose databases, literally hundreds of them, right? And it's impossible to cover all of them. So I'm trying to cover a few of them which are most important and give you context, right? So, okay, so with that, let's get into the section. So here, the assumption that I'm making here is most of you know about SQL and also know at least the basics of Python. Okay, so that's the assumption that I'm making, because otherwise this will, again, even if you don't know SQL and Python, you will be able to understand some of the details, not all, but some of the details. But if you know this, you have a better chance of understanding more of what I'm discussing now. And here is the whole agenda. Again, please understand that this is only an overview session, not a dive deep. If time permits, we will do more dive deep sessions or deep dive sessions in the future, right? Today, I'm just going to give you a big overview of a ton of special databases, both regular databases and cloud-based databases, right? So this is what I wanted to cover. Again, this is mostly about data stores. This is not about compute, right? For example, I've done a session called Big Data for Big Data Platforms for Machine Learning and AI. It's a live session that I've done publicly earlier. There we talk about Hadoop and Spark and EC2, all of those details in a lot more detail. So this session is not about compute, it's mostly about data storage, right? So that's very important for us to recognize, okay? So I'm just trying to set the stage. First is obviously relational databases. This is the database that most of you may have encountered. So if you look at some of our free videos in SQL, we use MySQL as one of the most, it is a very, very widely used open source relational database. There are also Oracle databases that you may have used or encountered. Also, there are cloud-based relational databases like AWS RDS. RDS stands for Relational Database Service, right? So first I'll cover the standard relational databases that all of you may be comfortable with, so that we are warming the stage, right? Then we'll go into flat files. Okay, this is a typical type of data storage that is used on Hadoop and Spark. And I'll give a quick overview about Pig, Hive and Spark SQL. Again, I've discussed this in one of the earlier sessions where I discussed about how to use Pig, Hive, Spark SQL from a compute standpoint, right? Here, I just wanted to mention this for completeness sake, because many of you might have your data stored on Hadoop or Spark, and you can access and perform a lot of data pre-processing and data analysis work using Pig, Hive and Spark SQL. So I just wanted to give you a brief of this. Then comes so this is your traditional relational databases. This is your flat file based storage, which is mostly in the context of Hadoop and Spark. Then you have all of these are your NoSQL databases mostly, right? So when people say NoSQL databases, they mean non-relational databases today, right? So very popular database. Again, there are hundreds of these NoSQL databases that I'm not going to cover here just in the interest of time. Okay, there is Cassandra, there is CouchDB, there are tons of them which are popular, which we cannot cover given the time constraint, right? The first and very popular NoSQL databases are called document databases, and I'll give a brief overview about MongoDB, right? Then you have in-memory databases like Redis and Memcache, which are very, very powerful, which are very, very useful, especially in the context of machine learning and AI applications. Similarly, there is a whole data structure called an inverted index, and there is a special type of data store. We don't call it a database, we call it a data store called Elasticsearch. You may have heard ELK stack, where E stands for Elasticsearch here. I'll talk about Elasticsearch and why it's useful, especially when you're designing a search engine, right? Then there are other special purpose databases and data stores for time series data, for graph data, etc. I'll give a brief overview of these, right? So again, we'll try to cover as much as possible in this live session. If you cannot, probably we'll have one more live session. We might overshoot a little in case time doesn't permit. If required, we'll do more live sessions like these, going in depth into one or multiple of these data stores themselves, right? So let's jump into the discussion. Again, I'll keep taking breaks in between, and I'll keep answering your questions on the live chat. So let's jump into it. The relational databases, again, relational databases is a semester-long subject in undergraduate level computer science, right? So this is a whole subject. I've also taught this recently for our computer science students and also for our GATE students. So this is one whole subject. It's a 6-month semester-long subject at undergraduate level. So I don't think I can do justice to this by trying to explain everything in 15 minutes, right? But I'll give you an overview. These are databases that started in 1970s, right? Oracle was the pioneer in terms of these databases, and Oracle as a company started primarily to build relational databases in the late 1970s, early 1980s, right? So all these are very popular examples of relational databases, right? Again, there is a whole area called relational algebra, but I'll come to it. You might have heard of Oracle databases like Oracle 11G, 18G, 19C. Again, there are multiple numbers here. Oracle has like a huge set of databases. Of course, while Oracle databases started off trying to be relational databases, now Oracle databases can do many other things apart from doing traditional relational databases, right? MySQL is an open source database. If you look at our free videos for SQL in our course, you'll see that we actually use IMDb data on MySQL to teach you how SQL itself works. Then there is SQL Server from Microsoft, very popular, especially in the enterprise world. Then there is PostgreSQL. This is again an open source database, just like MySQL, again very popular in the academic circles. Then there is IBM DB2, okay, a very interesting and DB2 is one of the pioneers of relational databases along with Oracle and SQL Server. Right? These are some of the most popular. Again, there are tons of relational databases. I'm just listing the most popular and widely used. So relational databases are based on mathematics called as relational algebra. Again, I'll not be able to cover relational algebra in detail, but this is the whole area. And many of you who have used relational databases might have learned about tables, right? So SQL is the most popular popular querying language. I won't even call it programming language. I'll call it querying language to query relational databases, right? So if you know SQL, you know what a table is. You know lots of operations like select, join, group by, all of these stuff, right? So everything that we have covered as part of our course and as part of the free content of our course related to SQL, we have talked about it in the context of relational databases, where everything is a table. Tables are the most important structures here. Then we talk about primary keys, foreign keys, all of that stuff is here, right? And the relational algebra is the mathematics behind SQL, right? Everything that you have in SQL can be represented using a mathematics called as relational algebra. Again, this is something the computer science students study both in undergraduate and graduate level, right? So again, this is not hard, but this is a very lengthy topic, so I'll not be able to cover into it. But whenever you listen relational database, actually in mathematics, a relation or in computer science in databases, a relation basically means a table, mathematically speaking, right? So relational databases are all about tables, and they're typically used for transactions. For example, imagine you buy something on an e-commerce website. That is a transaction, right? That's a transaction where you're buying something. Similarly, if you book a train ticket or a flight ticket, that's a transaction. If you buy something from a retail store, that's a transaction. If you use your credit card or debit card to purchase something, that's a transaction. So relational databases were the great databases. Almost they were like monopolies from your 1970s to early 2000s. To early 2000s, for almost 30-35 years, they were the kings, right? Because again, most of the use cases were for e-commerce, companies, flight tickets, all of that stuff, right? There is a whole area within relational databases called transaction management systems. Again, I'm not going to go into it, but I'm just giving you an overview, right? So what are the objectives? Why were relational databases designed in the first place, right? Relational databases were designed primarily for transaction-driven purposes. If you're buying a ticket or if you're booking something on an e-commerce platform, they're designed for transactions, right? And remember, they were designed, all of this mathematics and the early relational databases were designed in the 1970s, late 1970s, early 1980s. In those days, hard disk space was too little. People didn't have like the terabyte hard disk that we have today. I still remember days when we had 8 GB of hard disk space, not RAM, HDD. Okay, I still remember those days, right? So this is again in early 2000s, I saw 8 GB of HDD. Imagine in 1980s, hard disk was a premium commodity. So what they said was, whenever I'm storing data, I don't want to store duplicate data. So one of the most important objective of relational databases is, how can I save disk space while I'm storing this data? Because in the early days of computing, or in the early days of modern computing in the 1980s, what people wanted to do was people wanted to store data. So a lot of relational algebra, a lot of databases that you study in your undergraduate level computer science, one of the big objectives is to avoid any duplication of data so as to save disk space. That was one of the most important objectives, right? Again, things have changed. So I told you that relational databases ruled almost till early 2000s. But after early 2000s, right, especially around 2008 or so, right, things started changing. Even companies like Google started changing the whole scene of data storage in the early 2000s, right, around 2002, 2003, right? See, Google had to store the whole crawl of the internet. How do you think relational databases will ever scale to a problem like that? They would not, right? So in the early 2000s, things started changing, and also hard disk prices have started falling dramatically, right? Because of the falling hard disk space, people said disk space is no more important. What is important is speed. Again, in the early 2000s, as internet applications like search, e-commerce started becoming popular, even social networking in the mid 2000s, as internet applications started becoming more popular, people said, I want speed. I don't care if we have to spend more on disk space, but I want speed and reliability and scalability. Okay, that's what companies like Google, Amazon, Facebook brought to the table. These are new types of applications, right? So new types of applications came up with new types of data stores, new types of databases, right? So because the classical relational databases, the mathematics behind the relational databases would not scale to our new modern needs, right? So just wanted to give you that context here, that historical context. Now, again, if you don't understand some of these, that's okay. There are broadly two types of data structures that are used in your relational databases. Okay, we talked about indexing, right? When we learned about SQL as part of our course, which is also available in free videos, we talked about indexing because indexing is a way to speed up your select queries. If I want to select or if I want to filter something, if I want to filter data and get only few rows or few columns of data, right? Indexing can speed up these things dramatically, right? So indexing is basically an activity of constructing new data structures on your data store to speed up queries. So indexing as an idea came from relational databases. Similarly, there are special data structures called B plus trees. Right? Again, this is something that you study in your computer science databases course. Right? I'll not be able to go into the details of it. You might have learned this in data structures and algorithms courses also, but mostly people learn it in a databases course. A B plus tree is basically a special data structure that is designed to optimize disk reads and writes. Okay, I'll not, again, explaining B plus trees is a 2-3 hour topic in it onto itself, right? So I'm giving you a high level overview of where is what, right? So relational databases were the king till early 2000s because everything that we wanted to do were transactions, tables, operations like joins, filters, group bys, those were the important things. But remember, SQL is still a very, very powerful query language, which is even used today, right? So let's not forget the power of SQL, right? While relational databases are not useful in every scenario, SQL has been ported to make it useful in many real world situations. Okay, so this is the big idea. Now you might say, now you talked about cloud databases and self-hosted databases. Now what does this mean? Look at this. A self-hosted database basically means I buy a powerful computer, typically a server computer, and I install my database here, whether it's MySQL or Oracle, whatever it is. This is basically an in-house database. So this is on-premise, okay, which means in my office, I have a server room where I install this, where I have this powerful computer, which is a server with a lot of disk space. I install MySQL here. This is self-hosted. Okay, I'm hosting MySQL on my own server. Now, cloud databases, on the other hand, right? Again, this server itself, I can use the physical server that I have in my office, or I can borrow a server from Amazon or Google or any of these. So we discussed in one of the previous live sessions about EC2, right? EC2 is Elastic Compute Cloud. So you can literally rent a powerful server on Amazon AWS, and you can install MySQL on this. Like when you do this, what happens? You as the administrator or the installer of MySQL, you are responsible for optimizing MySQL. You're responsible for backing up data. You are responsible for everything. On the other hand, cloud databases, right, have become very, very popular nowadays. And the reason for this is, suppose imagine a world, right? Imagine if I want to create a database. I'll give you an example actually that will make life better. So we have a database to store all of our user comments or user data. Okay, we at Applied AI course, we have a database to use user data. So one way to do it is, okay, we borrow a computer from Amazon Elastic Cloud. Again, we host most of this on AWS, and I can install MySQL here, and I can store all of my data here. All of that stuff, I can do it. That's one option. This is self-hosted on a cloud. A cloud database, on the other hand, says, okay, don't worry about you taking a box from us and installing it. A cloud database basically says, just create a database. Okay, we'll create a MySQL database for you. You just query this database. We will look after everything in the backend. We will look after how much compute it requires, how much storage it requires, what backup it requires. All of that we will take care of it. So in a self-hosted or a self-managed database of your own, you have to do all the admin work yourself. Whereas on the cloud database, look at this. If I do this hosting myself, I need to hire a full-time database administrator to ensure that my MySQL server works well, because we have thousands of students that we have to cater to. On the other hand, if I say, okay, I don't want to do this, I'm willing to pay a small additional money, let Amazon take care of it. So today we use something called as Amazon RDS. Okay, RDS stands for Relational Database Service. So which gives you a MySQL server. And what we do, we just create a database there, we create our tables there, everything we do it, and let Amazon or AWS do all the administrative work for us. All the backing up, it takes care of it. Some of the optimizations also it can take care of it for us instead of us having to worry about it. So some of the database administrator work is being taken up by the cloud databases. That's why cloud databases are becoming more and more popular, and that's the reason for people to move from self-hosted databases to cloud databases to cut costs. And I can also scale. Imagine if I want to go from, let's say, 2,000 users to 10,000 users, my database has to increase, right? If my database size or my number of computers have to increase, or the size of my compute resources have to increase. Now, I need a full-time developer or administrator to take care of all of this if I'm self-hosting. If I'm using it on a cloud database, I don't have to worry about it. AWS takes care of scaling it. If I say, okay, this is how many queries I'll call every second, but I want to make it 10 times that tomorrow, it will scale immediately. So both in terms of cost and speed, cloud-based databases are becoming more and more popular. There is one place where self-hosted databases are better than cloud-based cloud databases, which is if companies say we cannot host our data on other computers, we need to host it on our own computers. Okay, for privacy, whatever reason. Again, security for cloud databases is also terrific nowadays. Okay, there are financial institutions which run on AWS, Azure, and Google Compute Platform today, right? So there are some companies whose policies say you can't move our data from our own offices to anywhere for security, whatever reasons. Again, American Defense Forces and Pentagon itself is planning to move to cloud databases. I think they have struck a deal with Microsoft Azure for that, right? So again, so I hope you got an understanding of why cloud databases in general are being preferred, especially by startups and even by large companies and government organizations over self-hosted databases. Now, having said that, what are the examples of cloud databases? There is something called as Amazon RDS, okay, Relational Database Server. Okay, so again, I've provided some links for you for your additional reading. So if you just click on this link, it will take you here, right? It will simply take you here. Okay, by the way, so I'll try to give an overview of 3 most popular databases. So you can just go to aws.amazon.com, go to products. If you go to products, there is something called as database. If you click on this database page, these are all the databases that are available on Amazon AWS itself. Again, I can give you more inputs about AWS because I have worked with some of these. Actually, many of these I've worked with while I was at Amazon, also for our own startup to some extent. So these are all the databases that are available, and I'll try to give you an overview of most of these, if not all of them, right? So then similarly, again, I was talking to you about Amazon Relational Database Service. What is an RDS? RDS basically says whether you want to use MySQL, whether you want to use PostgreSQL, or whether you want to use a Microsoft SQL server, or whether you want to use Oracle. Doesn't matter. Just come to our service and say, what database do you want? Do you want a MySQL database? We'll give you a MySQL database. You want a PostgreSQL? Yes, we'll give you that. There is also another database, Amazon's own database called Amazon Aurora. There are other databases like MariaDB, etc. All these are relational databases. So what Amazon RDS says is, whatever database you want, just come to us. We'll give you an instance of the database, use it, scale it, we'll maintain it, we'll do all the admin work for you. Just use it, pay us a small fee. Right? Simple as that. Similarly, Azure. Okay, so this is also a very nice page. This is Microsoft Azure. Again, I'm trying to cover AWS, Azure, and Google Compute Platform, the 3 most popular ones. So on Microsoft Azure itself, okay, so if you go to Microsoft Azure, go to products, there is something called as databases here. These are all the cloud databases. These are all the cloud databases that are available on Azure itself, right? So on Azure, if you see, there is Azure database for MySQL, right? So if you want a relational database, which is a MySQL in the back end, you just use an Azure database. If you want an Azure database for PostgreSQL, you can get that. If you want an Azure SQL database, this is a SQL servers database, right? Similarly on Google, okay, so if you go to Google Compute Platform, go to products, there is something called databases here. If you click on databases, these are all the databases that Google has. These are the relational databases like Cloud SQL, and there is non-relational databases. So if you go to Cloud SQL, which is the most popular of these because we have used it and tried it. So if you want a Cloud SQL, you can either get MySQL, you can get PostgreSQL, or a SQL Server. SQL Server is a Microsoft own corporate database, right? So you can get all of this. So what these companies have effectively done is, they're like, okay, If you guys are used to using MySQL, that's okay. We'll give you a MySQL instance. If you guys are used to using Oracle database, we'll give you an Oracle instance. SQL Server, we'll give you a SQL Server instance. You want PostgreSQL, we'll give you PostgreSQL, right? Whatever you want, use it. Just come to our platform, use our cloud database services, right? Now, the most important thing here is for loading data, for retrieving data, for modifying data, for querying data, because that's what we'll most likely do as a machine learning or a data science engineer, right? Or a data scientist. SQL is the most popular most popular language to insert, delete, modify, all of that stuff. So if you know SQL, you can use any of these relational databases with minor changes. So, like for example, MySQL has some additional functionality that Oracle may not have. Oracle has something called as PLSQL, which is a small modification to SQL itself, right? So as to write better programs, especially for Oracle databases. So every data store uses SQL. Every data store is compatible to SQL, but they will add some additional stuff on top of SQL, which are very fine-tuned to that relational database, right? So if you know SQL, you can use any of them. Like we have sample and free videos in our course for SQL. Please check it out. It's in the first module itself, where we actually show you how to install a MySQL server, all of that stuff. Like if you say, I don't want to install MySQL server, I just want to use a cloud server, all the documentation, it's very simple actually. It's about a bunch of clicks. You can go to RDS. Again, we have done a live session on how to create an EC2 instance using AWS. Something similar is there even for RDS. There are phenomenal tutorials on this page. Just go check it out. You should be able to create a simple, for all of them, not just for AWS, for Azure and Google Compute Platform also. It's very simple to create a MySQL database and use it, right? So that's one. Okay, so the next prominent type of data store is flat files. What are flat files? So if you recall, if you open a file, some of you who know C programming, right? You have this command called fopen, right? You might have studied this in your BTech first year or in the early stages of your higher education, right? You open a file and you write something to the file. Similarly in Python, I can write and read to files, Python, Java, whichever programming language you want. This is simply about storing data in a flat file, right? I'm just storing data, first column, second column, third column, first column, second column, third column. I'm just storing data in flat files, right? So this is again, when I store flat files on a single box, okay, imagine if I have my laptop or my desktop and if I'm storing all of this on a single box, I can just use any major programming language like Python or C or any language or Java, whatever language I have, to read and write to these files, right? So, but imagine if I have large amount of data, okay? So typically log files, like this is something that I've seen used extensively. For every transaction, for everything that you do on Amazon, right? There are log files that are created by the servers, right? These are literally huge amount. They're like petabytes worth of log files that are created on daily basis. These are just plain text files with some timestamp information saying, okay, at this time so-and-so activity was done by so-and-so user, blah, 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 blah. These are simple log files, okay? And these log files can be in CSV. We know what is comma separated value files or tab separated value files. Or more recently, people are preferring JSON files, right? So your file, how do you store your data? You can just store it as comma separated values, right? See, this is exactly like storing a table. We talked about CSVs and TSVs in our course also, right? So if you have a table structure like this, if you want to store something in a table, instead of storing it in a table, you say this value, comma, this value, comma, this value, comma, this value. That's what is your comma separated values. Right? So JSON is a very, very popular format which has become very popular again because of multiple reasons, and it is JSON basically, okay, let me go into this, right? So this is, okay, I don't have to, I already have this page open. So what is JSON? First of all, JSON was basically a JavaScript object notation. JSON was created in the context of JavaScript to store data, right? I've given this link in the document also. By the way, this whole document, I have shared it in the live session. So if you go below in this live session, so if you just go below in the description section, I have this whole document already shared so that you can look at the links also, right? So, okay, so JSON is a file format like this. It's a text file, remember. This is an example of a JSON file, right? So in a typical file, how do we store our data? Let's look at this. In a typical table, I mean, because I'm assuming that you know about SQL and tables, I might have a table like this. My first name, my last name, is alive, right? What is the age? All of those columns or fields, and for every person, I keep entering this data. This is how I store in tables. In JSON, what I do is this. JSON, okay, this is a very, very popular data format nowadays. What I do here is, I clearly mention what is the field name. Like for example, let's take the first row, row 1. This row 1 is represented by saying for row, so this parenthesis open, again there will be a parenthesis close at the end, right? This parenthesis close. So this parenthesis open to parenthesis close basically means first row. Within this first row, I have a column called first name, value is John. So everything is stored as key value pairs here if you think about them, or the field name and the value. Last name is Smith. The third one is alive is true, age is 27, address. Within address again there is street address, there is city, state, postal code, right? So this again, I've given a link to this. This is how JSON format looks like. Again, this is all a text file, don't forget that. This is a simple text file where the name of each field is followed by the value in that field for each row, right? So where is a document? Yeah, a document is here. Again, you can just go click here. Again, with this click, you'll just come to this example. Okay. Again, we'll see why this is useful when we look at document data stores, all of that stuff in a little while. Okay. But these are 3 popular ways of storing data. And I have seen a lot of companies, teams use JSON extensively. And if you want to create a JSON file or read a JSON file, Python, especially in more modern programming languages like Python, it's trivial to read it. Right? Now, okay, flat files are cool. When they're on a single box, you can just use Python to read and write files. But oftentimes, we have this on a distributed file system. In a single, see, look at this. If I have, let's assume 10 computers. Let's assume I have 10 computers that are connected via a LAN, right? They are all connected via a LAN, right? Computer 1, computer 2, computer 3, so on and so forth, computer 10. Let's assume each of them have a hard disk. Let's assume this has 1 TB hard disk. This has 1 TB hard disk, this has 1 TB hard disk, and so on and so forth. Imagine if the data that I have is, let's say, 5 terabytes that I want to store. Okay, this is not very uncommon, especially at internet companies. 5 TB is actually a joke. Okay, because we typically work at hundreds of terabytes of data or even petabytes of data, right? So when you have log files or when you have any data which is of this scale, how do you store this data? Right? What all you have is a bunch of computers that are connected to very fast Ethernet or LAN. So what we do here is this 5 terabytes, we'll split it into we'll split it into 10 512 GB chunks, and each 512 GB chunk we will store it. So 512 GB will store it here, 512 GB will store it here, 512 GB will store it here, so on and so forth, so that this whole 5 terabytes is distributedly stored on these 10 boxes. Right? Just like the way your computer has a file system to manage all the files, distributed computers use a file system called as HDFS. This is one of the most powerful and widely used file systems called Hadoop file system, Hadoop distributed file system. This is the most popular data store that is used as part of both Hadoop and Spark. Again, there are a lot of internals on how HDFS itself works, but I'm giving a high level overview of how it works. Okay. So when you have large amounts of data, it is split and stored across multiple boxes which are connected via an Ethernet cable, a fast Ethernet cable. Now, if your data is stored on HDFS as flat files, remember, there is no indexing, there is no special data structures, nothing is there here. Okay, all you have is simply JSON files or TSV files or CSV files. No indexing, because if you look at it, when I was discussing about, not this. Okay, so when I was discussing about relational databases, I told you that there are special data structures called B plus trees that are used to optimize disk reads and writes. Similarly, a lot of indexing is done to speed up queries. In the case of HDFS, it's just a file system. Data is stored in a file system, in a distributed file system. That's it. No indexing, nothing. Now, how do you now obtain data from this, from the HDFS, and do data pre-processing? One of the most popular languages there is called Apache Pig. Again, I've been very fortunate because I've seen the evolution of this programming environment called Pig at Yahoo Research. When I was there, it was being built, right? So what it does is it says, give me HDFS data, right? And I will be able to run, extract data, do some basic pre-processing, do all of that for you. No indexing, nothing. That's why this is slow. Pig is slow because there is no indexing, there is no attempt to speed up things. But Pig was very, very popular around, Pig I think became very popular around 2009, 2010, right? When it was being used by companies like Facebook, companies like Amazon, companies like Yahoo Research at that time. Tons of companies were using this, right? And Pig itself is a very simple language. If you know SQL, Pig is a cakewalk. Okay, Pig looks slightly different from this, but Pig is extremely simple. Again, I provided a link to Pig itself. If you look at it, let's look at this, right? So let's look at a simple 4 lines here. It says load data from so and so file. Then it says group by this. For each generate this. So we know about for each from Python programming, right? So we know about group by, right? So these are all, again, this is how Pig looks. Pig doesn't look exactly like SQL. Pig doesn't look like Python. It looks like a combination of a typical SQL program and a typical, it looks like a combination of SQL and some programming language. Pig is a programming environment on its own. But if you know, again, this document is something that I've used extensively. I mean, I must have read this document and referred to this probably hundreds of times in my own professional career, right? It's again, we have had people who didn't know about Pig, who picked it up over a weekend. I've had teammates like that, right? Who knew only SQL, because Pig is so simple. If you know any programming language like Python or Java, and if you know SQL, picking Pig is trivial, right? Again, I provided a link. If you want to use Pig and pick Pig, this is one nice document for your other. Again, it's extremely simple to pick it up. And you don't have to know lots of internals about HDFS, all of that stuff. Again, Pig became very popular because in the late 2000s, in 2009, 2010 time frame, there were very few engineers who understood HDFS, Hadoop, Spark, all of that. Because writing raw Hadoop code or Spark code is very, very hard. So researchers at Yahoo Research, they said, okay, let's build a programming language which is very similar to SQL, which many of our developers and engineers know, very similar to SQL, but slightly more powerful than SQL, which can work off HDFS without people having to write raw code in C, C++, Python, Java, all of that stuff. So Pig made life easy, and I've written hundreds of Pig scripts for data analysis in the early days of my career, right? So while Pig was developed at Yahoo Research, there was another huge development called Apache Hive. This was built at Facebook. Facebook said, okay, Pig is good, but Pig is very slow. Number one. Number two, Pig is not exactly like SQL. It's a huge modification on SQL. So Pig said, so Facebook said, okay, we will build something called as Hive. Okay, Hive is also a distributed data store on top of Hadoop, on top of HDFS, right? So HDFS stores all of its data, Hadoop stores all of its data on HDFS. So Hive sits on top of this, right? So Hive said, okay, we will have a query language called HiveQL, which is 95% similar to SQL. So if you look at Hive queries, they look exactly like SQL with a small modification. But Hive also said, why should we use just the flat files of HDFS? Let's build some more indexing functionality on top of it, so that Hive is going to be much faster than Pig and much more easy, not just for our developers, but for our business folks. Again, in a lot of top product-based companies, not just developers know SQL. I've seen sales folks, I've seen marketing folks who know SQL, because they have to actually crunch data. They have to actually make SQL queries to make business decisions. So Facebook said, okay, let's build HiveQL and Hive itself, which is significantly faster than Pig and which is much closer to SQL. And Hive today is one of the most widely used. It's open sourced, obviously. Hive is much more widely used. I've used Hive extensively myself at Amazon. It's still one of the most popular big data stores on Hadoop and Spark, right? Again, Hive itself is very simple. If you look at Hive queries, I'll show you an example here. Okay, so look at this. This is an example from Pig. This is how a Hive query looks like. Look at this. This looks exactly like a nested SQL query, right? Look at this. This is about drop table, all of that, load data, all of that stuff. But look at this line. This is the most important line, right? So select whatever you want. Again, within that there is select. This is like a typical SQL nested SQL. Sorry, this is like a typical nested SQL statement, right? So HiveQL looks very much like SQL with small modifications. Right. So again, I've provided a link to this in the document itself. So if you want to use Hive, it's extremely simple to get Hive, and learning HiveQL is much easier than even learning Pig. It's very much, it's 95% SQL, right? Next, what happened is Spark became, again, Hadoop was the pioneer in many ways on distributed data stores and data processing. Then came Spark. Again, I discussed about the differences between Hadoop and Spark from a compute standpoint in the previous live session that we've done, right? In one of the earlier live sessions that we've done. But Spark has something called as Spark SQL, where Spark says, okay, can I get the best of everything? Okay, Spark says, okay, this is built on top of Spark. Spark SQL is built on top of Spark. It says, I'll have all of the functionality of Spark. I'll have all the functionality of Spark, but you can write programs and mix SQL along with Spark programs written in Scala, Java or Python. And Spark uses something called as data frames. Earlier it used to be called RDDs. Now they are called data frames. These are very similar to your Python data frames or pandas data frames, right? They're very similar to your pandas data frames. They're just distributed data frames, right? And Spark SQL said, why should I limit myself just to connecting to HDFS? Spark SQL said, okay, I'll connect to any data store. Whether you give me a Hive data store, whether you give me a HDFS data store, whether you give me a relational databases, doesn't matter. I can execute Spark SQL on any major data source that I care about. So companies which use Spark SQL extensively. Okay, let me open up Spark SQL page here. Look at this. Okay, so look at this. This is very interesting example. Okay, some of you who may not know Scala may not be able to understand this, but it basically says, okay, look at this. This is your Apache Spark. This is your Spark SQL. Spark SQL sits on top of Apache Spark. Now Apache Spark can connect to any database. So some of you may already know about JDBC and ODBC that you might have learnt in your undergraduate days. JDBC stands for Java Database Connectivity. So if you have any database, okay, if you have any database, let's assume you have a MySQL database. Okay, let's assume you have any database. It need not be MySQL, could be any database. If you want to connect it from a Java program, what do? You have JDBC that is sitting in between. You talk to JDBC, JDBC talks to database, and all the communication happens to JDBC library, right? Since Spark is built using Scala, right, and Spark uses the Java runtime environment, right? Scala also uses the Java runtime environment. Any database in the world which you can connect using JDBC, you can connect it using Spark, right? Because Spark works on Java runtime and Java virtual machines, right? So the whole objective here is, again, you can connect to any database. You can connect to HDFS, you can connect to relational databases, you can connect to even non-relational databases nowadays, right? So now your question may be, should I use Pig or Hive, or should I use Spark SQL? If your company uses a Hadoop cluster, then my recommendation is, instead of Pig, my recommendation is to use Hive. Because Hive is faster, it's much more easier. This is my recommendation from my own experience. But you can also use Pig. Nothing stops you from using Pig. Pig is slightly slower. That's the key. Now, if your company uses Spark, just use Spark SQL because it gives you everything, right? Now, you might wonder, what is this useful for? Applications where you have hundreds of terabytes of data or petabytes of data. Okay. Anything which is a few terabytes of data, you can use relational databases today. There are some relational databases that can even scale to tens of terabytes of data. But if your data storage is in hundreds of terabytes or petabyte scale, you should prefer to build everything on Hadoop or Spark, because, and you should, I mean, if you're using Hadoop, I would recommend you use Hive. If you're using Spark, I would recommend you use Spark SQL, right? So if your data scale is actually in this range, then Hive and Spark make a lot of sense. They're the only options that you have, to be honest with you, right? So these are two important ones. So I'll answer a few questions and then take a quick break before we dive into the rest of the session. So, okay, let me answer a few questions. PostgreSQL, I mentioned about PostgreSQL, right? PostgreSQL is also fairly popular. It's used by, okay, let me change to webcam. Okay, so PostgreSQL is something that is used by a lot of academic institutions, also used by a few companies. I've seen that. So is big data necessary for data science? Not always, because not every company has these big data stores, right? But if you know Python and SQL, you should be able to pick up ways. See, what is data science? Data science is all about acquiring the data that you need, right? So big data is all about acquiring the data that you need, and just give me a second. Okay, it's all about acquiring the data that you need, doing a bunch of pre-processing, and then building data science machine learning models on top of it, right? Now, if your data is stored in a Hadoop cluster, you'll have to retrieve the data using something like Hive. And the beauty of most data stores today that are available is most of them are compatible with SQL. So you have to know SQL very well. So even if you don't know how Hive works internally, all of that stuff, there might be a database, there might be an admin who is managing a Hive cluster. You just write your HiveQL query, which is mostly like SQL query. You retrieve all the data and then you do all of your processing after that, right? So what is important is knowing all the internals of how Hive works, how Hive builds indexing. That is mostly not necessarily for data science folks. That is mostly what software development engineers and big data engineers should know about, right? Most data science folks should know how to query this, how to query data from these data stores, which you can do extremely easily using SQL and modern programming languages like Python, right? What is the difference between Spark SQL and Spark? So Spark is the whole distributed compute platform. Okay, you can write code in Spark using Scala, which is a functional programming language. You can write it in Java. You can also write it in Python, right? While Spark SQL is built on top of the Spark platform, so that the end users like you and me, data science folks, we don't have to write Spark code, because writing Spark code is much harder than writing SQL queries. So what Spark SQL is doing for us is Spark SQL talks to Spark itself. It's like an interface between Spark and data scientists like us, wherein if I don't know how Spark works, if I don't know how to write Spark code, I can just use Spark SQL, write SQL query, which is very similar to standard SQL queries that we know of, and it will retrieve all the data that we want, right? So I hope Spark SQL gives us an SQL interface to process and to retrieve data. Spark itself is a much more complex distributed compute and storage platform that can do much more than that. Okay. So many are saying there is no scope for data science. Is that true? I would argue the other way. So today we have more companies that are that are looking to hire from our students than the students who are completing the course any given week. So we do this on a weekly basis. So we get so much of requirement from companies because they have hired a few students of ours. They like the students. They're like, folks, we want to hire 10 more guys. Do you have people? We're like, okay, some of the students are completing. Just give us 1 more month. As soon as they complete, we will send them to you, right? So the problem is the other way. The problem is there aren't enough good data science and machine learning folks while the market needs tons of them. This is what we observe. Okay. So how data store is different from database? Again, I'm using the word data store because databases typically is a word that is used to mean relational databases and NoSQL databases. HDFS is not a database. HDFS is a data store where I'm just storing data, right? So I'm using the word data store. For example, inverted indices, something that I'll discuss a while later. It's a data store. It's not a database, because databases typically mean your tabular relational databases or NoSQL databases. Data store is anywhere where you can store databases, including a database, right? So, okay, sounds good, folks. Give me 5 minutes. Let's take a quick 5-minute break. I'll just pause the video here and I'll be back after a quick 5 minutes break, and we'll continue with the other data stores, right? So what do we have now? So let me put up the next slide for you. The next slide for us is document stores. Okay, we'll go into document stores. Again, I'll try and cover document stores, in-memory databases, inverted indices, and special purpose databases today. I might overshoot by a little, but if you all can cooperate, we'll try to finish as much as possible, right? So just give me a couple of minutes, I'll be back. Okay, folks, I'm back, and yeah, so let's just start in a minute or so. I just forgot to get my water bottle. Okay, so let's look at the comment section. If there is something I can, okay. So this is a very good question that Narsim has asked. Will NoSQL databases like CouchDB, MongoDB replace traditional SQL databases? Not always. To be honest with you, I have seen cases where relational databases are hard to beat. Okay, they're really good. Like for example, e-commerce transactions, right? Again, the reason why we have these NoSQL databases is each NoSQL database has a special purpose behind it. Whether it is speed, or whether it is to store documents, or whether it is for IoT applications, or whether it is for search, they all have specific niche applications, right? And relational databases, the traditional relational databases, are still extremely powerful, right? Otherwise, companies like Oracle would have died by now, right? Things like MySQL would have died long back. Actually, on cloud services like AWS or Google, I don't know about Google Compute Platform, but on AWS and Azure, the most popular database service is actually the relational database services, right? So I think they are nowhere close to dying. They're extremely powerful, but there is scope. See, this is like this. Earlier, we only had relational databases for all tasks. Now there are specialized tasks for which non-relational databases make much more sense, right? Especially because we want speed, or we want, I'll give you some examples like data store, etc., right? Or maybe we want extremely wide tables where most of the stuff is going to be empty, whatever it is. I'll give you some examples while we go through it, right? So difference between Hadoop and Spark, before that, why Pig is good even if there is no indexing? Because to be honest with you, when you have, again, indexing is time taking. If you have raw data on your raw flat files on your HDFS, why not use Pig, right? If you want to do one ad hoc query, if you're doing some data analysis, you're doing some ad hoc querying, right? Then Pig works fairly well. Again, it is slow. Let's be realistic there. It is slow, but I mean, if you don't do some specialized queries that require indexing, that require speed, why not just do Pig? Again, there are Pig is more so SQL is the Pig is easier to write code in, actually. I mean, that's what I feel than pure SQL or HiveQL. Again, maybe I'm biased because I've written Pig queries for so many years, for almost 10 years now. So I like Pig, but I also dislike its lack of speed. So I use both Pig and Hive. I also use Spark SQL here and there. Okay. Okay, somebody is asking about Python and Spark, right? So, sorry, Hadoop and Spark, not Python and Spark. So, Hadoop is the earlier of the distributed platforms, and Hadoop became popular when RAM was small but disk space was large, right? So, the intermediate results, that are computed are always stored on disk and not in RAM, in Hadoop, right? So Spark came along. I think Spark became popular in 2012, 2014, right? Hadoop became popular around 2008, 2009, right? So there is almost like a 7-year gap, and Spark was designed and built at Berkeley, one of the great places for distributed systems and operating systems. So what they did was, around the 2013, 2014 time, the size of RAM was also increasing. So Spark said, why should all the intermediate results be stored on disk like Hadoop? If we can store it in memory, let's store it in memory, right? So Spark tries to use the growing amount of RAM on our systems much more efficiently than Hadoop itself. That's the basic difference. That's why Spark tends to be faster than Hadoop if you have more RAM on your boxes in the distributed system. That's the core of it. Again, there are many more details that we can go into, but we'll have to get back to a discussion, right? So, okay, where are we here? Yes, so we are back here, and okay, so let's jump into document stores, right? So when many people say NoSQL, they often mean document databases as NoSQL, but document databases are one type of NoSQL. Now in SQL, see, in the traditional relational databases, everything is table centric. Everything is about a table. In a document database, this is not table centric. This is something called as document centric. I'll explain you what is document centricity in a couple of minutes and why document centricity is very useful, right? So since this is not table centric, people said this is not like SQL or not like traditional relational databases, right? So now what is a document? Okay, that's the first question that you have. Okay, I'll give you some, again, MongoDB is one of the most popular document databases out there. I've given some reference links here. Now what is a document? A document is a JSON file. It's a text file or an XML file. For those of you who don't know what is XML, okay, let me just show you this. I think I have it open here. Yes. So this is your JSON file, right? I've showed you JSON file. What is a JSON file? JSON file has these curly braces in which I have, see, this is what is a document. So remember, in your traditional databases, you have tables, right? You have tables. You have multiple tables. Each table has multiple rows, and you join tables. If you recall, you join tables to get more data. And why did you split the data between tables? To avoid duplication of space, to save space. That's a core objective of relational databases. In something like a document store, everything is a document. So this is a document. This is document 1. A document, typically in modern document stores or document databases, it's stored as a JSON file. Okay, so it's not in a table, it's a text file, and this is what is called as one document. You can store, so if you want to think about it, a row in a table can be thought of as a document because this is all the information that you will store typically in one row here. Right? So you can either store it in JSON file, JSON is one of the most popular ones, or you can store it in XML. If you remember, XML looks very much like HTML, okay, with contact. So this is within contact, there is first name, last name, phone, cell, phone, work, there is address, all of this type. Again, XML was very popular in the early 2000s, but slowly people moved to JSON, right? But most document stores today let you either use XML or JSON. There are other ones also. There is BSON, which is binary JSON basically, and things like that. Now, okay, this is one of the best pages. Okay, this is from MongoDB documentation. What is a document store? Okay, so first of all, what is a document? Okay, let's look at this. So typically, this is one of the best diagrams. I think I have this diagram. Yes, I have this diagram here. Okay, so look at this. Okay, so I'll come back to this statement. Schema fields are dynamic. For example, okay, let me answer this actually. Suppose if I have a table like this, okay, for a person, okay, let's assume I have multiple columns, first name, last name, all of these things. Suppose this is my table 1, okay. Now, there might be some people, suppose there is person 1 here, there is person 2. Tomorrow, if you want to add a new column here, let's assume I want to add a new column. Let's say a grade, okay. Suppose this column didn't exist. If I want to add a new column, I can add it in relational databases. When I add it in relational databases, let's assume for person 2, I give grade A. For everybody else, it will be null. because for everybody else it will be null, which means see, when I have a column like this which I'm adding later, or if I have a column where only very few of these rows have a valid value, most of these are nulls. I'm just wasting space here. I'm simply wasting space here if I store everything in one table. Number one, right? So to avoid this, what do? We create a new table. Okay, let's assume there is also an ID. Okay, let me show you this example. Okay, so let's assume I have only one large table. Okay, let's call it table 1. Okay, so same table, I'm just drawing it here. ID, a bunch of fields. So let's assume there is a field called grade, a bunch of fields. Okay, single table. So let's assume only for a small subset of rows here, only for some of them, the grade is available. For most of them, it is null. So what is happening here? There is a lot of wastage of space. So in relational databases, what do? We change it into two tables. What do? We create two tables, table 2 and table 3. Right? What do? In table 2, we store all these fields except grade. So we have ID. We have all of this. We don't have grade here. So we create one more table where we have ID and grade. Right? For any person, if I given an ID, if I want the grade, what do? We join these two tables. Right? We join these two tables. We do something called as an inner join, if you know SQL. So what does relational databases say? Relational databases say, if you have a column which is mostly empty, break this into two tables and use join for most of these tasks. But what is the problem with join? Joins are expensive. Imagine if I have to compute a join of these two tables. For every column with this ID, even if it is indexed, I will have to go and check for this and then combine them. So joins are very, very computationally expensive. But relational databases ask us to do it because relational databases try to optimize disk space. They try to optimize disk space, not necessarily the speed. Right? This is one of the biggest flaws of relational databases. Relational databases says, okay, you can join the table. But imagine if the data is humongous, internet scale data, joins can be extremely expensive. Imagine if I have 1 million rows here and if I have 100 rows here. Look at the cost of joining all of them, even if I have indexing. If I don't have indexing, it's worse off, right? So what document stores says, why are we storing information in two tables? Why can't I store everything in just one document? Problem is solved, right? So again, this is a very, very nice diagram. Again, I've taken this diagram from MongoDB's documentation. Let me just see, is there a hiccup of any sort? Just give me a second. Oh, I forgot to screen share. I'm sorry, folks. I'm sorry, my bad. Sorry, my team just reminded me that I need to screen share. Sorry. My bad. I'll repeat this. My bad. Extremely sorry. I'm extremely sorry. I'll repeat everything. Okay, my bad. I just lost it. Okay. So you have your document databases. Okay, I'll repeat the document databases. I'm very sorry about this. Screen share. Yeah, I hope I've done the screen share, right? So yeah, the screen is shared. Let me just verify that everybody can see the screen. My bad. Just give me a second. Can everybody see the screen now? Let me just verify, my bad. Okay, everybody can see the screen now. I'll repeat the document store part, no problems. I'm sorry. So, okay. So let me just stick to the screen itself from, right? So document stores are not table centric, they're document centric. So now what is a document? So here I have the links here, right, that I just showed you. Okay, so what is a document here? A document, you can store a document using JSON that we have seen, and each row. Okay, so I think I have the drawing here. Yeah, okay, I've drawn a lot without realizing it. Sorry, my bad. So so this is what I was trying to tell you. So this entry here that you have, this first name, address, hobby, everything, this is document 1, right? So typically what you want to store in one row is what is typically referred to as one document. You can store it either using JSON or using XML, and the grade is in another table. And for any user, if you want to know whether grade exists and what the grade is, you typically compute join. This is what relational databases say. Why do relational databases say that? Because they want to optimize disk space. They don't want to waste space storing nulls, right? And relational algebra and relational databases say you can always use join operation to combine these two tables and get whatever you want. But the biggest problem with join is joins are hyper expensive in the real world. Why are joins expensive? Think about them. Imagine especially in the post 2000s, where internet became popular, where most data is generated on the internet. If I have 1 million entries here and if I have 100 entries here, just joining these two tables can become very expensive even with indexing. And 1 million is a joke. For most internet companies, you can expect this number to be 100 million, and this number may be even 1 million, right? So this whole thing is basically breaking this large table into two tables to optimize for disk space at the cost of compute, at the cost of speed. Your joins are terribly slow, especially when the data sizes are large, right? So this is a problem with relational databases. Now how do document stores avoid that? This is one of the best pictures. Again, let me just verify if everything is all right for everyone. Okay, so everything is all right. Okay. So for MongoDB, okay, look at this. For MongoDB, this is a very nice example from MongoDB. So typically imagine there is an ID, there is some information, there is some ID, some information, some ID, some information, some ID, some information. Okay. Now this data, if you use the traditional relational databases concept, okay, you're storing the data, you're splitting the data about one person called Mary Jones, whose ID is 1. You are splitting it into 4 tables, and you'll have to join all these 4 tables to get all the information about this person called Mary Jones. Now if the table, okay, so the reconnection is successful. Let me just check on the live itself. I think there might be a small gap here. Please excuse that. We should be back. Yeah, we should be back. Yeah, I had a small interruption, so I'm back here. Is this better now? I'm back. Just let me know if we are okay. Then I'll continue. Okay, you should be able to see the feed now. Let's give it a couple of minutes. I think we should be back live. So is everything all right, folks, now? Can you hear me? Can folks confirm that you can hear or you can see me? Or yeah, we can see now. Okay, sounds good. Sounds good. Yeah, I just... yeah, you can see the screen also, I guess. Is everything all right? Can you guys confirm if everything is all right now? Let me just, not yet, okay. Yeah, that's why I've changed the wireless connection that I'm connected to. Let's see, it's not yet fixed. Okay, I guess you can see me now. I think the connection is back to stable. Let's wait for a couple of minutes because my internet speed is pretty good. I mean, it constantly shoots above 60, as most of you can see. Let's wait for a couple of minutes. Yeah, 64 Mbps is pretty decent speed for most of these requirements. Let me just update. So can you hear me now? You're able to hear me? Good. Okay, I think it was my streaming software that gave up on me. So working fine? Okay, we can continue from wherever we left off. Is this okay now, folks? I can see your chat comfortably. Okay. Now it's good. Okay, thank you. Good job. Good. Let's get back. Okay, now you can see without any interruption, right? So where did we stop? We stopped here, right? So let's get back to the discussion where we stopped. So, okay, let me go back and verify if everything is all right. Everything is cool? Okay. So I might overshoot this session by a while, but please be patient. I promise you I'll fix it for you. Okay. So let's continue this. Okay. So let's go ahead with this. Okay. So in a relational databases, what did we do? To save disk space, we broke up this big table into multiple smaller tables, right? But if I want to get all the data for a person called Mary Jones, I have to join these 4 tables, which can be very, very expensive. And why did RDBMS do that? Because disk space is more important in the 80s when the whole concept of relational databases started off. What MongoDB says is, okay, why should I do it? Today, when MongoDB was designed in the early or mid 2000s, I think they started in around 2007 if I'm not wrong, mid 2000s to late 2000s, they said, why should we do that? Today, disk space, we have hundreds, we have like terabytes of disk space. Disk space is no more a problem. Speed is important, right? So we have more disk space today, and disk space is very cheap, right? And what we want is fewer expensive joins. Compute, I want speed. I don't want to wait for joins to happen. So MongoDB says, let us try to store this data in a very logical fashion. It says, I will create one document here. This is one document. I'll create one document for this person called Mary Jones. All the information about this person will be stored in this document only. Look at this. This is the beauty of a document data store. All the information about a person is going to be stored in just one place in a very logical manner. This is how we intuitively think about it, right? How do we intuitively think about data stores, right? We intuitively think about data stores this way, right? Again, I've taken this from the MongoDB web page itself. So why should we use document data stores over relational data stores? Because the data model is very intuitive, right? Again, my schema or my table structure, I can change it whichever way I want. How can I change it whenever I want? It's very simple. Today, let's assume for these users, I want to add one more field. What can I do? I can just add one more field here. Let's assume I want to add a field called grade. I'll just add a field called grade and I'll say A for all the users who have a grade. For the users who don't have a grade, I will not even have this whole field. But in the relational databases, I have to create another table, right, which has ID and grade, and I have one more table to join. I have to join 5 tables now, not 4 tables. So MongoDB says, since space or disk space is no more important because it has become extremely cheap, and we want speed, we want to get a view of a customer, or we want to get a view of each logical entity like a person here in one single shot. They said, let's use document stores, right? It's a very, very ingenious idea in databases, right? Again, it uses JSON. You can query. Okay, let's go back to this slide here. This is the crux of the relational versus document stores. Now you might say, but is it fast? So what MongoDB did was, on a document store, they gave you the ability to perform indexing. Okay, so just like in your traditional relational databases, they also have indexing so that it's fast to query this database. It's also extremely scalable on cloud-based databases. Right? It's extremely scalable. I can add, suppose if I have one box on which I have a MongoDB, I can add one more box, and both these boxes can work together to increase the size of my database very, very fast. Right? Now, how do you insert data into a, look at this, how do you insert data into a MongoDB? How do you retrieve data into MongoDB? All of that stuff. There are 4 operations called as CRUD operations in MongoDB. Okay, so let's go to this page and look at that. Okay, so I think we have this here. CRUD operations basically mean, CRUD basically stands for, okay, so let me open this. Create, you want to create a document, right? You want to read the data, you want to update data, you want to delete data, and you want to do bulk write. So CRUD, C-R-U-D, these are the 4 operations for which MongoDB is heavily optimized for, right? And if you want to write data into MongoDB or read data into MongoDB, you can do it using any major programming language. There is something called as PyMongo, Mongo. This is basically how do you perform CRUD operations, create, read, update, delete operations on a MongoDB using Python. Okay, let me just check if everything is working well. Okay, yes. Okay, so you can actually do everything in MongoDB using Python, using PyMongo. Again, this is a very simple tutorial for this. It's actually very, very simple. Look at this. If you want to add some data, you just say your database is called posts here. Okay, to this you want to insert a document. A document is one logical entity that you want. So it has a function called as insert one. Right, here you created a JSON. You create a JSON, you insert it. Right, similarly you can retrieve one. Very simple. There are literally like 5 or 6 most important commands, and you can just install PyMongo. Very simple to install. You can just install it using pip. Right, once you install pip, once you install PyMongo, you just say import PyMongo, and you can just, that literally this document is good enough for you to get started with PyMongo or with MongoDB. Right, again, there is no, to the best of my knowledge, I don't know an SQL interface, but I've used PyMongo extensively. It works very, very well. Right, so what is it giving you? It is giving you, when you have data like this, when you have data where you might have to break the data into multiple tables to avoid duplication of data in a traditional relational database, it's better to use a document DB, because all the data about one entity here, like called Mary Jones, is stored at one place. So no joins. It will take more disk space because I'm storing the first name for Mary Jones, for someone. There is more disk space, but so what? It's giving me more flexibility and speed. Nowadays we care less about disk space and more about speed, and that's why MongoDB is very powerful. It has indexing, scalability, all of that stuff. Now on the cloud, if you want MongoDB, what do you do? Again, you can download MongoDB, install it on your laptop, try out everything. But if you want to do it on a cloud, you have AWS Document DB. So if you just go to AWS Document DB here, okay, I don't think I have a link here, but you can just Google. So this is the link. You just go to Document DB. It gives you a MongoDB instance. AWS Document DB gives you a MongoDB instance as if it's a MongoDB instance on your laptop. It's just that it's stored on a AWS cloud. Similarly, Azure has something called as Cosmos DB. Right, so let's go to Cosmos DB and show you. So Cosmos DB is very interesting because unlike AWS MongoDB, Cosmos DB says whatever database you want, whether you want MongoDB, Cassandra, these are all the types of NoSQL databases. Whatever database you want, I can give you any database. Just like the way the relational databases said, I can give you MySQL, I can give you PostgreSQL, I can give you whatever you want. The Azure Cosmos DB is very interesting because it says you want MongoDB, I'll give you MongoDB. You want Cassandra, I'll give you Cassandra. You want proper core SQL, I'll give you core SQL. You want other types of data stores, some of them I don't know, to be honest with you, I'll give you those. Right? So it gives you everything that you want. Okay. So this is the crux of why document databases, which is one of the most popular types of NoSQL, have become very popular in the internet age. Right? Again, you might, in the real world as a data scientist or a machine learning engineer, you might have data stored in MongoDB. That happens. I had to work with MongoDB because some of the teams that I was obtaining the data from stored it in MongoDB. What do? I install PyMongo, get the data that I want. That's it, done. Next comes in-memory databases. Okay. So there are two very, 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 very popular in-memory databases called as Redis and Memcached. I've used both of them in the real world extensively. Now, what is in-memory database? Okay, let's understand that, right? Most databases store their data on the disk because disk is where you have most space. In-memory basically means in your RAM, in your main memory. If your data is stored in main memory, you can retrieve it much, 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 much faster than disk. We all know that, right? We all know this. We all know this fact that, okay, let me just check if everything is again working well. Okay, so everything is working well. Okay. Somebody says key value. I'll come there. I'll come to what key value is. So in memory basically refers to the fact that everything is stored in RAM. Okay, so everything is stored in RAM, right? So now people said, okay, if everything is in RAM, I can access this data much faster than if it is on disk. Traditional databases, including document data stores, store data on disk. So Redis and Memcache, one line representation of them is they are distributed, which means all this need not be stored on one box, because one box may not have enough RAM. But I could have 10 boxes. I could use the RAM on all the 10 boxes. Together it could be big. I could have, let's say, a 16 GB RAM box. And let's assume I have 10 such boxes. I have 160 GB of total RAM across all these boxes. So Redis and Memcache are distributed. They are in memory, which means they try to store all of the data in the RAM itself as much as possible. They are also key value stores. And what are key value? In Python, we have something called as dictionary. In standard computer science, it's nothing but a hash table. What is the purpose of a hash table? I can search in a hash table in order of one time. This is something that we discussed in our Python chapter, right? Dict is an implementation of hash table in Python. So these are data stores where the search time is extremely fast. It's order of one because it's in the main memory. It's no more on the disk. They try to keep everything in memory and they are distributed, which means you can scale them. So why are they useful? If you want to read something very, very fast, or if you want to write anything or update something fast. In machine learning, let's assume you have a feature for a person. You want to build a model, let's say. Let's assume you want to build a model. You have these features. This whole data, let's assume for each person you have an ID corresponding to it. Let's assume you have an ID. Okay, let me just use a diff. So let's assume you have a big table like this, right? Where you have an ID and feature 1, feature 2, so on and so forth, feature 100, right? Now you want to apply a machine learning model, right? To apply a machine learning model, you need the features. So you get an ID from, let's assume you get the user ID. I take all the features, I pump all these features into a machine learning model. The machine learning model gives me some output, which I use to make a decision. Now, if I store this whole thing in a traditional relational database, in a relational or document database, this whole thing may be stored on disk. If it is stored on disk, it might be slower to retrieve this information. On the other hand, if I store everything in Redis or Memcached, right, which are in-memory data stores, which means that this whole thing is going to be stored in the RAM in the distributed fashion, right? Now, given an ID, see, if I use my ID as key, right? If I use all these feature values as value, a concatenation of all the feature values, if I use it as a value, this is now like a dictionary. This is the key and this is the value, except that this is in memory and distributed. This whole table, this table could be large. For Amazon, this could be 200 million rows, right? Because there are close to 200 million customers for Amazon worldwide. Right? Now, in such a case, all this need not be stored in one box. It could be distributed across multiple boxes in a distributed environment. Redis and Memcache automatically do this for you. You give it an ID, it gives you all these features in just like 2-3 milliseconds. You can get all of this data in just a single digit milliseconds, which you can send it to your machine learning model, which will apply whatever model you're training, it will give you output. Right? So your in-memory data stores or in-memory databases like Redis and Memcache are extremely useful for low latency machine learning applications, either to store features or to store weights. But typically for storing weights, you can use a simple dictionary. You don't require a distributed hash table. But for features, distributed hash tables are very useful. Similarly, in-memory databases are extremely useful in real-time streaming applications. Imagine, because this is stored all in memory, if I keep getting some request and if I want to count how many times this user visited my pages, what do? I'll just have a feature here called count. Whenever a user visits a page, I just go, I increment it. Because this whole thing is in memory and I can go to the corresponding row very fast because the key is the ID. I can edit or I can keep track of very fast flowing real-time data using an in-memory database, right? So Redis and Memcache are extremely powerful in-memory data stores, right? So another big application of in-memory data stores is for database caching. Now, what does database caching mean? Look at this. Let's assume this is my traditional database. It could be a document store. It could be a It could be a relational database. Suppose suppose this user or a programmer or a data scientist ran an SQL query. Suppose I'm trying to retrieve some data. When I retrieve the data from here, let's assume I'm trying to retrieve the data from here. I write a SQL query, I get the data back, I use it. But imagine if there is another user who might also run something very similar to that query, right? But next user, when he goes and queries, the database has to redo the same work again and again. Instead of that, the search results of the database, if I can store it in memory, in a Redis, or if I can cache these results in memory, this user, when he queries it, he can directly get the data from the Redis data store, which is much faster than going to the traditional databases, because these databases store data on disk, right? So again, in big data architecture, Redis and Memcache are also used to cache database search results, right? Again, if you want to learn about Redis, you can insert, edit all the data on Redis using any of these programming languages. You can literally write in every major programming language under the sun. Okay, you can, if you have a Redis instance, you can insert data, delete data, all of that in any programming language. Python being one of them. Within Python, there are tons of PyRedis is something which is very popular. There are tons of APIs. There are tons of libraries which you can use to talk to Redis itself. And Redis and Memcache are so powerful that all the major cloud platforms have them. So AWS has something called as Elastic Cache, where you can either create a Redis or a Memcached instance. Azure has Azure Cache for Redis. Google Compute Platform has Cloud Memory Store. Okay, so if you want it on the cloud systems are available. You can just click on this. Again, these are simply Redis. Okay, and you can use Redis or Memcache, or you can insert data, delete data using any major programming language, including Python. Okay. Next comes a very interesting thing called as inverted indices. Very, very interesting, very, very powerful concept, right? So let's go. I'm just cross-checking if everything is all right constantly, just to ensure that there are no hiccups again. So what is an inverted index? Let me give you an example. Okay. Again, this is one of the best examples and diagrams I've come across on the internet, and this is taken from Hitachi Vintara's website, right? So on search, this is web search, right? On web search, I have a lot of documents or web pages. Let's assume this is the data on one web page. This is the data on another web page or another document. This is another on another web page or document, right? Now what do? I remove all the stop words. This is my stop word list. Given this, I remove all the stop words and I create this table. And what is the table that I'm creating? Look at this. Okay, I'm creating an ID. This term here is best. For best, I created an entry. And I'm saying best is available in document 2. This term best occurs in document 2, right? Similarly, I'm creating another entry called blue. Again, all these are, if you notice, they're alphabetically sorted, right? The second word that I have, again, from these documents, I've removed the stop words. We discuss about what stop words are in our course videos, right? So basically, most often used words like a, and, which are not very meaningful. So the bright, look at the word bright. Bright, so there is an entry for this word bright, and we say bright exists in document 1 and document 3. It exists in document 1 and document 3. So this is called inverted index, because what am I doing here? I'm creating an index here wherein I have every word, and I have the numbering of the documents in which this word occurs, right? Look at this. It's called as inverted index because I have an index which has all the words. For every word, I have the number of the document in which this word occurs. Now, why is this very useful? Look at this. Imagine if I have a search query word called bright butterfly sentence. Suppose this is my search query. Now, I want to find documents where both the words bright and butterfly exist. How do I do that? Right? Suppose if I don't have this inverted index, I have to go through each of these documents and search if bright is there, butterfly is there, and that will take a lot of time. And I could have millions of documents like this. On the other hand, if I have an inverted index created, what can I do? I'll search for bright here because this is alphabetically sorted. I can easily find bright here. And I know that bright exists in document 1 and 3. Next, I look for the word butterfly. Okay, butterfly I know exists in document 1. It doesn't exist in document 3. Now look at the intersection of these two. What is the intersection of these two? Document 1, which means now I know that in document 1, the word both bright and butterfly, both of them are there. So if this is my search query, document 1 is most likely a good search result as compared to document 2 and document 3. It's simple, very simple. This is a data structures part. Inverted indices are a concept in data structures in computer science, which are extensively used in search. Now, this is a very simple toy example. Imagine this with billions of documents where the inverted index itself is humongous, that it has to be stored. Again, we want to store this inverted index in memory, right? And we want to store, of course, this whole, look, imagine Google search or even Amazon search for that matter, right? With thousands, millions of products on Amazon, this inverted index can be humongous, right? So this will be stored in a distributed fashion in memory. But what is being stored here? The inverted index is being stored. Now, how do you do it? Again, I have been fortunate to work at Amazon Search, the team which works on Amazon Search very closely. And Amazon Search, like most search engines, uses an inverted index to speed up query. Again, in addition to this, they do a lot of machine learning. This is one of the basic data structures that they use in addition to a lot of machine learning and deep learning, right? So to speed this up, again, what do we want? Let's not forget what we want here. What we want here is a distributed in-memory inverted index which can scale to billions of documents, right? Now, what gives you that? So, in an earlier time, there were software which were open source called Apache Lucene and Solar. Okay, very popular open source software for building inverted indices and search engines. They were very popular from mid 2000s. From mid 2000s to almost 2000, I think 2013-12 tak, right? They were very, very popular. Then came something called as Elasticsearch, which is also an open source software, which is also managed by a startup called elastic.co, which is the most powerful, inverted index search based facility that is available today, right? So today, again, some people do use Lucene and Solar now, but if you're trying to pick something to build a search engine, especially the inverted index part of search engine, it's best to use Elasticsearch, right? And there's a company called Elastic which will help you do that. Again, you can query Elasticsearch in many programming languages. I've seen it being used. So Amazon has something called as Cloud Search, which gives you a Lucene or Solar instance, while it also has something called as AWS Elasticsearch, which gives you an Elasticsearch service. And these are actually used by a team called A9 at Amazon, which is responsible for all of search. So these systems were built by A9, Amazon search team, and it is used and it's open to everyone so that you can also build your scalable search engines, right? Very simple. So inverted indices is one type of data store primarily designed to make your search faster. That's the goal here, right? Now there are other special purpose databases, right? So there is something called as, again, I have not used some of these special purpose databases, so I'll not be able to go deep into it because I have personally not used them extensively. I've read about them but not used them extensively. So there is something called as time series databases. One good example is something called as AWS TimeStream, which they announced very recently, right? Which is specifically designed for IoT applications and which is primarily designed to perform time series operations very efficiently. Suppose if you want to take the fast Fourier transform on some time series data. Suppose you're collecting data from, let's say, some heartbeat monitors and you want to compute FFT on it, right? Or if you want to do any time series analysis on it, right? You want to do some advanced time series analysis on that. Storing the data in a way to facilitate faster time series operations is the objective of time series databases, primarily designed for IoT applications. Again, I've taken this diagram from Amazon TimeStream. Their objective here is if you have TimeStream data, whether you're getting it from chips, whether you're getting from Alexa-like devices, or you're getting it from transportation devices or industrial equipment, whatever it is, you can just dump all of the data into Amazon TimeStream. And on this data, you can build phenomenal, again, the beauty of this is they give you SQL-like interface. You can also write code in advanced languages like Python to analyze all of this SQL time series data, and you can build machine learning predictive and anomaly detection models on these time series using this. So here time series data is stored very specifically in a special format to make analysis and machine learning modeling on time series data much more efficient. Okay. Again, to be very clear, I've read the documentation for time stream, but I've not used it myself. So, so feel free to read it and learn more and educate us also. Next comes graph databases, right? This is also a special purpose database. So there is a database called as AWS Neptune. Again, other cloud platforms also have it, but I don't know them very well. That's why I'm only referring to AWS Neptune and AWS time stream that I know of. Now again, you can find the documentation here. Again, there is a lot of data which is graph based. If your data fits into the graph format, whether you have social networking data or recommendation system data or knowledge graph data or fraud detection data that you can represent as a graph. These are 4 big applications. Again, Amazon knows this very well, right? So if you have data, again, recommender systems, as we discussed in our course, you can represent it using a bipartite graph, right? You can represent it using a bipartite graph like this, right? Social networks, we all know there is a social graph. We know about knowledge graph, all these things. So wherever you have these special purpose, okay, let's go to Amazon Neptune page and see what they say about it. So let's go here. So this is Elastic Cloud. This is Lucene. Okay. This is Cloud Search that I talked to you about, Amazon Time Stream. Okay. So this is graph databases. Again, you might wonder, why do we need special databases for graphs? Because there are special operations that you want to perform on graphs, right? Suppose you want to run the page rank algorithm on a graph, or you want to find the distance between 2 vertices in a graph. Suppose you are my friend. Suppose this is me, you are my friend. You have a friend whose friend is this. Suppose I want to compute the distance between this person and this person. The distance is 3. Right? This is a graph operation, right? Or if I want to recommend similar products, I can pose it as a graph problem. So there are a lot of real world systems which can be represented using graphs. Search itself can be represented, or PageRank is one type of search algorithm on graphs, right? So if you have graph data, you can use Amazon Neptune, and the objective here is, again, they have special use cases like social networking, if people use and like all of that stuff. You can recommend friends. Again, this is something that you can build very easily. Again, recommendation systems, fraud detection and knowledge graphs, all these sorts of stuff. So again, I have not used Neptune extensively. I have read about Neptune, and I've read about Gremlin also, which is the other very popular graph database. And these databases are special purpose databases when your data is represented as a graph, right? So in a nutshell, the core idea, coming back to our whole agenda itself, right? We have understood what relational databases are, what flat files are, where do Spark, Pig and Hive play an important role, what are document databases and why do we need document databases in the modern world, in-memory databases, especially for feature storage for machine learning and AI applications, inverted indices for search, and special purpose databases for special needs, like if you want to store time series data or graph data, right? This is the broad overview of all again, this is not the big set. There is something called as columnar data stores, which I have not gone into, right? There's a whole area called columnar databases, right? Which have not, like there is something called as Vertica, which is supposed to be very popular here. Again, I've not gone into some of those other databases. I've gone into some of those that I've mostly used, or some of the special purpose ones that you might be interested in, right? So that's the whole goal here. And sorry for the couple of hiccups that we have faced in the last few minutes. So yeah, apologies for that, but thankfully we could finish everything in the 1 hour session, right? So sounds good. Okay, if you have any questions, I could answer some of them for the next 5-6 minutes, and then we can take leave, right? So yeah, if you have some questions, please feel free, and I'll try to answer as many as possible in the next 5-10 minutes. So somebody says, okay, so let me get into these questions. Okay. Oh, somebody says if you want to use AWS, again, you don't have to set up the instance yourself. So if you go to this, so if you go to AWS Elastic Cache, so if you want Redis, right, you can just go to this Amazon Elastic Cache for Redis. They give you a Redis instance which you can start using. You don't have to set it up. Again, the whole objective of this whole scheme is, as I mentioned earlier, right? So we want to move away from self-hosted databases and data stores to cloud-based, because they help us lower the admin responsibility, scale gracefully, reduce costs and improve speed, right? So for many of these databases that I discussed today, there is an availability of readily available cloud storage. For Amazon, you have this. For Redis, you have Amazon Elastic Cache. So you don't have to install it on your own box, right? So how helpful data engineer experience in Azure and Hadoop in learning data science? Again, if you know Hadoop, if you know other big data technologies, that's great, right? Knowing more never hurts, okay, to put it bluntly. If you know more, it's always good. But if you don't know, that's okay, because if you, so for example, let's take two candidates, right? One candidate who knows all the big data technologies but doesn't know what is hypothesis testing, or doesn't know how deep learning works, or doesn't know about Adam algorithm in deep learning, right? In the deep learning optimization algorithm. Versus another candidate who knows about hypothesis testing, who knows about Adam, who knows SQL, but who doesn't know big data. Okay, most companies will hire the candidate who knows machine learning and data science for data science and machine learning roles. Because if you know SQL and Python, you can easily pick up all these big data technologies, because you're not going to work as a big data developer or architect. See, if you're looking for a big data developer role or a big data architect role, you have to know these big data technologies inside out. But if you're looking for a data science or a machine learning role, just knowing how to use them, how to extract data from them using SQL or Python is more than sufficient in 99% of the cases, right? Okay, sounds good. So let's look at it. Can Pandas data frames be used to do what Spark data frames does? Not exactly, because Spark data frames are distributed data frames. Okay, so they're not stored on one box. You see, where does Spark become powerful? If you have large amounts of data that you want to crunch in a distributed environment, Spark data frames play an important role. There used to be something called RDDs earlier, but Spark moved away from RDDs to data frames because people know about data frames from Pandas. Pandas data frames are a single box data frames. They're very powerful when you're working in a single box environment, but if you're working in a distributed environment, Spark data frames are way, way more powerful. Okay. So where are we? So somebody says to take a class on AWS. Actually, you can look at the live sessions. I think sometime March or April of 2019. You can just go to our channel. There are earlier live sessions. Just go through them. I've given an overview about big data in AI and machine learning, and also about AWS itself. How to create an EC2 instance, how to install the software that you need from that. I've discussed that in one of the previous live sessions. Please check it out. If you're a registered student, you can just go to the desktop app. On the live sessions, there is something called AWS for machine learning and AI. That video is surely there. But if you're not a registered student, you should be able to find it in one of our previous live sessions that we have done. I think it's in March or April of last year. So Manoj, you're talking about ML internship opportunity at Applied AI course. This year we haven't specifically decided on it. As and when we decide on it, like we had something last year, we had something before last year also. We are still planning this. As and when we have an official announcement, we'll surely let you know, and we'll post it on YouTube itself, right? So you'll easily know as soon as we have an internship announcement made. For Redis and cache, if you want to make things persistent, it's not very hard. You can always, so everything that is in memory, you can always have one more thread which will dump all of the data into disk to make things persistent. That's doable, and that's actually done in practice a lot, because you don't want, suppose if one of your computers goes down, you don't want everything to be lost because everything is in memory. So Redis and Memcache facilitate a feature wherein whatever is there in memory, you can have one thread which constantly at a slower rate dumps it to disk, just so that in case of any power failure, things don't break down. Okay. Okay. So somebody says you worked as a DBA for 3 years, MySQL. What is the opportunity in data science and machine learning? One good thing that works for you is you know about databases very well. So you know how they work. And if you can learn the mathematics, the machine learning and the deep learning required, we have a lot of database people who come from the database domains and software engineering domains. I'm sorry. We have successfully graduated into data science and machine learning roles. One big advantage is you already know how to tackle with data. That's your biggest advantage. So unlike a typical Java developer, you know more about data storage, data manipulation, and I'm assuming you're much better at SQL queries, especially complex nested SQL queries, which makes your life, especially when you have to build a data pipeline, or more specifically when you have to do data analysis, you can do it much better than a typical Java or a Python developer. How much programming knowledge is required for machine learning? You certainly need to know the foundations of all of a major programming language, preferably Python, because that's the most extensively used. You have to know SQL for sure. You have to know the most important data structures which are available in Python, and you have to know the most important libraries. For example, you have to know Matplotlib, you have to know Pandas, you have to know SciPy, NumPy, very important libraries in Python. You have to know preferably some couple of machine learning libraries like TensorFlow, XGBoost, Scikit-learn. These libraries are very, very important in addition to basic knowledge of Python itself, right? Yeah, so yes, Python data frames. There are implementations of Python data frames that can work in distributed environments, right? So in such a case, yes, again, Spark is not just data frames. Spark is also the compute layer on top of it, right? So if you just have Python data frames and not compute platform, you will have to implement the compute platform yourself, making your life very, very hard, because implementing distributed systems algorithms is a nightmare. I used to write, I have written some distributed systems platforms, distributed system code using something called as MPI and PVM. This is much before Hadoop and Spark. They're so damn hard to write code in. Trust me, I've been there. Okay. So Hadoop and Spark make your life much more simple. It's not just about data store, it's also about the compute layer. The previous distributed system compute platforms like MPI and PVM are much, much harder to write code in than Hadoop and Spark, right? So, okay, folks, sounds good. We've overshot by a few minutes, but thank you all. Sorry for the couple of hiccups that we have had, but I hope you have had some understanding, at least a high level understanding of all the important data stores and cloud systems and why we go for cloud and other big data systems. And yeah, so please let us know if you want us to conduct more live sessions like this. Please share your ideas on our email address. You can just go to appliedaicourse.com. We have our email address at the top left, which is team@appliedaicourse. We'll try to conduct some of these live sessions to benefit everyone. Additionally, if there is something that we could not cover in this live session, please shoot your email and we'll try and answer as many as possible, as fast as possible. See you. Bye-bye.